It is my pleasure to introduce the first speaker of this morning, Yoshio Nishimoto, who's going to talk about some recent developments in CASPT2 and RASPT2 gradients. Yoshio, are you there?
Yes.
Can you share your screen, please?
Okay. But one moment, please. I think this is okay.
Full screen, perfect. We can hear you. So you have 20 minutes, including questions. The floor is yours.
Thank you for the introduction. And also I'd like to thank the organizer for giving me the opportunity to present recent my activities. So I'm going to talk about this title, Analytic first-order derivatives of multi-state variants, which is implemented in OpenMolcas already.
Yoshio, can you speak up a little bit?
Really? Is it okay now?
Volume of your microphone, please.
I think, is it still too, I'm speaking loudly, but.
Okay. We are maxed out here, right? Yeah. Right, it's hard to hear in the back, I suppose. Yeah.
Really?
Because I don't think we have any way to improve our volume here, right?
I think it's on maximum already.
Yeah. Try to speak now.
How about now?
Yeah, it's a bit better. Okay.
On Zoom, the sound is fine. Oh, thank you.
Okay, let's try this way.
Okay. Okay. Sorry for that. Yeah, I cannot speak loudly. I'm too tired. So as an introduction, I would like to say that energy derivatives are very important for quantum chemistry because with energy derivatives, we can optimize molecules, in particular with gradients. And if possible, we want to have analytic derivatives because numerical derivatives are very time consuming. But it is usually difficult to develop analytic derivatives with highly accurate methods like CASPT2. But in the last year, I think I presented this study because I implemented analytic gradients of single-state CASPT2 and RASPT2 in OpenMolcas. And last year, I think, yeah, I optimized these molecules using this active space, RAS 16 or 20 electrons in 20 orbitals. And I compared with RAS SGF, RASPT2, and some DFT calculations. And at that time, I didn't implement anything for analytic derivatives of multi-state CASPT2. But yeah, in this year, I would like to report this one, analytic first-order derivatives of XMS, XDW, and RMS-CASPT2 and RASPT2, meaning that we can now optimize, we can now locate minimum energy conical intersections, which is abbreviated as MECIs, with CASPT2 levels. And for example, this is a result with XMS CASPT2 for ethylene. And we can identify this kind of cone-shaped potential energy surface. So before going to the expressions for derivatives, I have to explain something about multi-state CASPT2, although I think audience is very familiar with it. So single-state CASPT2, we cannot reproduce the avoided crossing of, for instance, lithium fluoride. But with MES-CASPT2, we can reproduce the avoided crossing. Yeah, because single state CASPT2 does not consider the interaction between states. But to include interactions, we have to first construct the effective Hamiltonian and diagonalize it. But the problem is MES-CASPT2 cannot be applied to MECIs, because I will show the result later, but with MES-CASPT2, the potential energy surface is very distorted. So to fix this non-invariance problem, we usually use this XMS-CASPT2, which has been proposed by Shiozaki 10 years ago. And in the case of MES-CASPT2, one term of the zero-soda Hamiltonian is like this. This is derived using a diagonal approximation. But the better definition is like this. This does not use diagonal approximation. The left and right projections are different. This is XMS-CASPT2. And in the actual implementation, we first rotate the zero-soda reference states, and we derive this kind of the expression, which is similar to MES-CASPT2. So yeah, with XMS-CASPT2, the potential energy surface is very smooth. But the problem is now the Fock operator is different from MES-CASPT2, different between MES-CASPT2 and XMS-CASPT2. This F alpha and FSA is different. The difference is how this Fock matrix element is constructed, and in particular, this one electron density matrix is different. In the case of MES-CASPT2, the density matrix is completely state-specific, while in XMS-CASPT2, the density matrix is averaged over all states, like in CAS-SCF. So, yeah, Stefano developed this extended energy weighted CASPT2, which we usually abbreviate XDW CASPT2. This density matrix is weighted averaged using this formula, like the weight is like a Boltzmann factor. And he also developed the rotated multistate CASPT2, RMS-CASPT2. This uses the state-specific density matrix as in MES-CASPT2. But as in XMS-CASPT2, the reference states are rotated. So as a short summary of these MES-CASPT2 variants, I could summarize like this. So MES has a problem of rough potential energy surface, but XMS, XDW, and RMS may be fixed using by rotating the zero-soda wave function. But there are also differences between density matrix used in the Fock operator. So as a result, MES-CASPT2 cannot be applied to conical intersections, and XMS-CASPT2 may be very fine around the conical intersection. And we are not very sure about XDW and RMS-CASPT2, although Stefano has already investigated. So with these four MS variants, I implemented analytic derivatives in OpenMolcas, and I have to explain some equations which are rather complicated. So I use the Lagrangian multiply method, which is proposed by Helgaker and so on. And I first formulate or define the CAS-SCF Lagrangian, CAS-SCF Lagrangian and PT2 Lagrangian. This is just a sum of the constraint conditions in SCF. So this is a generalized Brillouin condition and MO molecular orbital also normalization, and this is CI condition, which are all zero. But the derivative of them may not be zero. And we also have to define the second order perturbation part of the Lagrangian. And the first term corresponds to the energy if alpha equal beta. And there are also 4 constraint conditions, which are all zero. But the derivative of them are not zero, not always zero. So using these Lagrangians, we can develop some other equations, but everything is too complicated to explicitly write. So just an expression. So we first have to solve this lambda equation because all RMS-CASPT2 variants are not variationally minimized with respect to T amplitude. So we have to solve this lambda equation. And after solving this, we obtain the lambda, and then we can take the partial derivative of the PT2 Lagrangian with respect to orbital and CI rotation parameters. This is very tedious to implement. And then we solve the z-vector equation as usual. And after solving this z-vector equation, we can calculate the gradient and interstate coupling vectors by taking the partial derivative of the Lagrangian. So this is a gradient which is useful for geometry optimizations. And this is the interstate coupling vectors, which is used for locating conical intersections. How? So I implement it, and I think almost all important features are already developed. And if you are interested, then you can check this CASPT2 gradients branch. But still, the symmetry constraints cannot be used, and the IPA shift cannot be used. These are difficult for me. And yeah, I'm going to show some computational results, which are very easy calculation, I think. So first, we have to check the potential energy surface of these methods. And I first optimized using all these CASPT variants, and I draw the potential energy surface by displacing along the gradient difference vectors and interstate coupling vectors. And as you can see, and I explained earlier, the potential energy surface of RMS-CASPT2 is very distorted. Yeah, please don't use this for MECI. But XMS, XDW, and RMS are all good, in my opinion. And also I checked the energy difference around the conical intersection determined at CAS-SCF level. And again, this RMS-CASPT2 behaves very strangely as expected. But XMS, XDW, and RMS are mostly fine. Although we can see some discontinuities in this RMS-CASPT2, but it is mostly fine. And notably, this is a crossing point at CASSF level, and we can say that MES-CASPT2 and RMS-CASPT2 are very similar. But the RMS-CASPT2 is much smoother, gives much smoother potential energy surfaces. So if you want to do MES-CASPT2 calculations, I think we should use RMS-CASPT2 as an alternative. So since I have also developed the RASPT2, the derivatives of RASPT2, I check the quality of it. And it seems that this cone shape is well reproduced, or the shape is at least okay. And the difference of the energy around the CASSF conical intersection is also smooth. So I think RASPT2 can also be used for conical intersection search. And I also located some structures of benzene. And yeah, there are seven MECIs, I located 7 conical intersections using CASSF, XMS, XDW, and RMS-CASPT2. And the largest difference between CASSF and XMS was found in this MECI2. And the difference is like 1.3 eV, which is very large in my opinion. And this is the excitation from S0 to S1. And the experimental excitation energy is like 4.9 eV. And XMS is the closest. And RMS is like underestimate by 0.2 eV. But maybe, yeah, this is still within unexpected accuracy of multi-difference perturbation theories. So in principle, we can use any kinds of MS variants. And I also checked the dependence on the state, on the number of state averaging, and taking the n state equal to as a reference, I checked the dependence of the excitation energy and the relative energy between S0 and MECI energy. And if I increase the number of states to be included, yeah, XDW CASPT2 behaves a little strangely, but compared with n state equal to 2, the maximum difference is like 0.4 eV. But on the other hand, XMS and RMS-CASPT2 behaves a little less vulnerable to the number of n states for excitation from S0 to S1. On the other hand, if we compare, if we calculate the difference between S0 and MECI energy, the XDW and RMS-CASPT2 are very, it's not vulnerable to the number of states. It's very stable. So overall, RMS-CASPT2 is not very strongly dependent on the number of states to be included in the average. So if we have to average many states, maybe RMS-CASPT2 is useful. And so this is a little more difficult to do because the active space is a little large, 16 electrons in 13 orbitals. But I did this kind of calculation. And this is dioxethanol, and we can find some stationary points from this minimum to the dissociation channel. And I identify, this is not my calculation, but I located these minima and conical intersections, and the energy is compared here. As you can see, if we compare the CAS-SCF and the CASPT2, the energy difference is like 10 kilocalorie per mole for these right three items, structures. And also, if we compare the bond lengths, CAS-SCF may underestimate, CAS-SCF underestimated like by 1.2 angstrom. So the structure may be qualitatively different in some cases. So this kind for this kind of large active space, it is useful to use restricted active space. And I did some calculations using XMS, RASPT2, and CASPT2 using a smaller active space. But yeah, it's difficult to use RASPT2 because the SCF convergence is little not, it's not as good as CAS. But anyway, the performance is like this. Maybe smaller CAS is better. It's difficult to make full advantage of RAS, at least for me. Hi. So as a summary, I developed analytic derivatives from XMS, XDW, and RMS-CASPT2 and RASPT2 in a development version of OpenMolcas. And yeah, they can be used for locating conical intersections, and RMS-CASPT2 is the least vulnerable to the number of average states. In future, I think, yeah, I need to do some performance improvement because the number of AOs is still limited, and I definitely want to avoid a strange loop structure, and other things may be done, possibly. And I would like to thank Roland and Stefano because they helped me a lot in the development and for all. Thank you very much for kind attention.
Okay, thank you, Yoshio, for the nice talk. So let's see if somebody has some questions. Luca?
Oh, hi. I'm just curious to understand what's the difficulty in using RASPT2. I mean, is a technical difficulty for the code, or it's more about choosing the right orbitals for the right RAS spaces?
Yeah, choosing the RAS space is difficult in my opinion because in terms of the development, nothing is difficult. Yeah, almost nothing was difficult, but you know, SCF convergence is a little poor than CAS than the case of CAS, so it's difficult, and it takes time because it's not as efficient as CAS.
Yeah, of course, of course. Okay, thanks.
Thank you.
Other questions? No one in the chat. So, well, in the interest of time, let's thank Yoshio again and move on to the next step, to the next speaker.